Now we have learned enough to formulate the equation for the motion of a rigid body. So today we will write down the Newton-like equation of motion for rigid body, and next day we'll see how can we do the same thing using Lagrangian formalism. So the kinetic energy of the rigid body. So how do I write the kinetic energy of the rigid body? Let's see. Let's ask that question. So see, rigid body motion, as we have discussed using Chasse's theorem, is a translation. So there will be a kinetic energy because of that translation. So I can write that this way. And you can choose the vector x to the center of mass. So capital M is the total mass. This is just the way we talked about two body central force problem. But there remember that the distance between the two bodies were not fixed. They can change, but here it is fixed. So that is because of the translation. And then I will have one part which is because of the rotation of the rigid body. So let's call that TR. And this I can write in terms of any three parameters. I choose to write phi, theta, phi and psi here, which are the Euler angles. So the rotational part, so this is translational part, and this is the rotational part. They're separated. If you look at the potential energy, the potential energy also has a part because of translation and a part because of rotation. It can be separated out in most cases. Not all cases though, but in most cases, say for example, the translational thing is coming because of a force like gravity, and the rotational thing is coming because of a force like magnetic field. What the magnetic field does, if you remember from your elementary courses on electrodynamics, is that if you have a dipole, it rotates the dipole. So this potential energy is that type of potential energy, which can be say like mu dot v. Mu is the dipole moment and v is the magnetic field. And this translational energy is, the translational potential energy is more like the potential energy which comes because the force is given by gradient of a potential. So this is more like f dot dr integral. Okay, that's just an example, but that is what we state at this point. And now because these two sectors are separated out, so I have a rotational sector. So even in the Lagrangian, then I will have a rotational sector, a translational sector, plus a rotational sector, and the rigid body motion analysis of a rigid body motion becomes extremely simple. In that sense, that I can just separately work out the equation of motion for the translation and rotation. Okay. Now, before we go further, we kind of know that the entire rigid body rotates together, but we like to put it in with a proof before we go further, because it will be quite useful later on. So how do I prove that? So the question we are asking is, does the entire rigid body rotate together? The other way to say is the following, that I have this rigid body and I have some origin here. So this is my space set of axes, this is my origin, and I consider one vector which goes to a point 1, I call it R1. So this is point 1, and I have another vector which goes to some other arbitrary point 2. So these 2 points can be any 2 points in the rigid body, preferably not the same point. And I call this vector which goes from R1 to R2 as small r. Okay. Now none of these points are the points with respect to which the rigid body is rotating, preferably. Then let us ask the question, if the angular velocity of point 1 is omega 1, the instantaneous angular velocity if you wish, and the angular velocity here is omega 2, then are these two velocities same? If the two velocities are same, we have chosen point 1 and point 2 at any 2 points in the rigid body. So then I will prove that essentially the angular velocity at any point is same. Now how do I do this? So I first look at the rate of change of the vector 2 with respect to the space set of axes. Now this point 1 and point 2 are two fixed points in the rigid body, means that if I wish, I could have put them pencil marks in point 1 and point 2, and they doesn't change. So the vector r is always fixed with respect to the rigid body. Okay. So now dr2 I can write as dr. I should have used the small r's because that's how I have defined them. So this is dr1 plus small r. Now I have a vector of a vector. Okay, anyway. So d bar d this with respect to s plus I'm sorry, this is dr, right? It's just vector addition, r1 plus r is r2. So here we are considering rotation with respect to the point 1. So point 1 is fixed, with respect to that the body is rotating. So if that is the case, then when I write this in terms of, so let me write this in terms of body axis first. This plus r1 is fixed because I have rotation with respect to that axis. So what I will get is omega cross r. I could have written this here itself. Right? Now this is 0 because there is no motion, no translational motion if you wish of the vector r with respect to the body set of axes, because r is said, small r we said that it's fixed between these two pencil marks. So the pencil marks cannot move in the rigid body, then the body will not remain rigid. So what I get is dr2 dt s is dr1 dtv plus, so this is a rotation with respect to the point 1, so I call it omega 1. The rotation instantaneous angular velocity I call omega 1, so it's cross r. Now I do the same thing with respect to the, I calculate this when the rotation is with respect to 2. Okay, now what will it be? You see that everything is same, all the analysis is same, only when I write these two terms I have to write dr2 minus dr, because that's what is r1. So this will remain as it is. We'll just have to change r1 to r2, but because of that minus sign, this will get a minus sign. So this r will become minus r. And now I'm talking about rotation with respect to 2.2, so I call that omega 2. And now if I compare these two, I get omega 1 equals omega 2, which essentially proves that all the points in the rigid body rotates together. So remember what we did. So there's a motion of this body which is in concern, and the motion can be a translation plus a rotation. To analyze this motion, first we consider any point r1, and we said that okay, so I will consider the translation of r1 and then with rotation with respect to that. Okay, so if I have now any vector r2, that can be written this way, and it turns out to be the translation of r1 as we expected, plus an effect which is coming from rotation, which involves the angular velocity with respect to the point 1. Then we did the same thing, putting point 2 fixed and asking the question, what is the angular velocity of 1? And that is omega 2. And we exactly calculated the same thing. So we can choose this way, you can obviously choose any point to which I will calculate the translation and rotation with respect to that point. So that's what I'm doing here. So the translation of the point 1 plus the rotation about the point 1, and here translation of the point 2 plus the rotation about the point 2. Now these two are equivalent viewpoints, obviously. And then if I compare these two equations that I get from these two equivalent viewpoints, I get that the angular velocity that I get of the point 1 with respect to 2 is same as the angular velocity of point 2 with respect to 1, which essentially tells that all the points in the rigid body has the same angular velocity. Right? Nice. So now which means that for the rigid body, we need to consider only one instantaneous angular velocity. Now, that is all right. What is the angular momentum of the rigid body? See, we are going towards the dynamics. We need a momentum to do the dynamics. We know angular momentum of a particle. Let us try to generalize that to a rigid body. Well, the rigid body is made up with many particles. Let me call the angular momentum as capital L vector. It's made up of many particles, and for each particle, this angular momentum I define with respect to any point in the rigid body, which is kept fixed and the rotation is considered about it, just like we did a little while ago. And the radius vector to any point in the rigid body from this point is say r. Say to the ith particle, the radius vector is r. So the angular momentum of the ith particle will be Ri cross the linear momentum, which is the mass of the ith particle times the velocity of the ith particle. So I am calculating from the origin in the body set of axis. So this Ri is from the origin of the body set of axis. So we can imagine for the time being that there is no translational motion. We are only considering the rotational motion. And let's see what is the velocity for the rotational motion only. It is omega cross r. So if there is no translation which is coming because of this, then Vs is just omega cross r. So I can replace Vi, which is the velocity of the ith particle, as omega cross r. Keep mi here, so this becomes Ri cross omega cross Ri. And this omega, as you can see, is taken to be same for all points in the body, and that is what we have just proven here. So that is all right. So you can take that to be same in all points in the body. What is the x component of the angular momentum? Let us calculate the x component of the angular momentum. So x component of the angular momentum, because this will give us some insight. So what is this? So let's ask that question. Okay, so this is mi. So remember that there is a summation over I which I have not written here. Sum over I implied. This is a little bit of difference. There is a little bit of difference with respect to the Einstein summation convention, because there is I is coming here 3 times, but this is our notation for the time being. We have implied a summation over I in all this discussion to come. So now this is Ri cross A cross B cross C, which you know already. So it's B times A cross C. So B is omega, so the x component of that will come here. And A cross C here is nothing but x square, sorry, A dot C is r square, which is nothing but x square plus y square plus z square, minus C. C is r, and the x component of that will come. So x component of r is just x. And then A dot B, so which is x omega x plus y omega y plus z omega z. It's x component. I can write it in a little different form. I can write this in the following way. And remember that I should have suffix I for all of these, all the places where I write x, y, and z. Right? So I can write this in the following way. I collect the coefficient of omega x together, and that is You see, I have xi square omega x here, so xi square is gone. So I have yi square plus zi square times mi, this entire thing into omega x, plus, write with a plus sign. Here I have, for omega y, I have mi, xi, yi. So this is times omega y, plus I get minus mi. So y has x and y. Sorry, this should be, yeah, it's all right. Okay, so this is what is Lx. Now I can write Ly and Lz, so that's your homework. Once you write all these three, you will realize that L, if I write as a column vector, this can be written in terms of, write this with prime, let's see why. A matrix which looks like this. And you can fill up the rest. Times omega x, omega y, omega z. Or if I write a shortened notation, L can be written as I omega. And there's one more step that one need to do. Here when I summed over I, so when we summed over I, to get the angular momentum L of the entire rigid body, we consider it discrete. So the number of particles is very large, so you can take a continuous limit where, say, mass or sum over the mass can be written as a volume integration of the density. If you do so, then you can write the ijth component of the moment of inertia tensor. So this is called the moment of inertia tensor. Check whether it is symmetric or not. Symmetric or anti-symmetric, or you cannot say anything about this. Check that. But I can write this as this also. This is straightforward to see, so I'll not prove for you. You can check yourself. Rho times. This comes just from whatever we have done directly. Once we take the Okay. See, for example, if ij was, so let's see what is ixx. Ixx is integral over v rho r. If I equals j, this term survives, otherwise it doesn't survive. So in this case, it survives. So this is x square plus y square plus z square minus I equals to j, and that I have chosen x, so this is just x square dv. So this is v rho r y square plus z square dv. So what was Ixx? Ixx was the component of Wx when I write Lx. Component of Wx was y square plus z square times mass, and that is what you get here. So rho times dv is kind of mass, but remember that when I do the integration, rho depends on xyz, so I have to really do the integration. So there also I have to do the summation. So this is one example, Ixx. And what you are doing here is, I have a density. So whenever I have a density, I multiply it with one of the variables, one of the independent variables of the density, and integrate. That's called taking moments. So moment of rho, or if I say nth moment of rho, it will roughly be dv rho x to the power n. Okay, that is one of the nth moment of rho. So here I am taking the second moment because I have y square, z square type of thing. I am taking it in a very particular way. So this is the second moment of inertia of rho. Why moment of inertia? Because rho is what is mass. Density, which is mass, is sometimes also called inertia. Okay, so I is the moment of inertia tensor. Now I is a tensor. This can be diagonalized. Which means that then I just have this diagonal component, and now I call them I without a prime. So these are all primes in my definition. Now how do I diagonalize I? Rotate the axis such that is diagonalized. See, I is calculated in terms of a particular set of axes. So that's what is y and z. Now axis, that's a axis in which I am, so say I have a body like this, I choose a set of axes which looks like this. So this is my body set of axes. Okay. And in this system, this xyz axis system, my moment of inertia is not diagonal. Okay. Moment of inertia tensor is not diagonal. Now, if I rotate the body set of axis and choose this in a certain way, that the moment of inertia becomes diagonal. So, okay, so it messed up with things. Let's call this is all right. such that the moment of inertia tensor becomes diagonal, then what all I have done is I have rotated the axis, right? Which means that there exists a spatial coordinate system for a rigid body where I is diagonal. Now, if I choose this to be my body set of axes, then calculations become a lot easier. We'll see it shortly. So first of all, if I have a L, now so this is called the principal axis. This axis is called the principal axis. Special for a given body. Depends on how the mass is distributed in the body. As you can see that I have drawn the three axes in this particular body in this particular way, because if you actually calculate for such a body, the principal moment of inertia will be along these three axes. Okay? And this is also called the principal moment of inertia. What's the advantage? Well, let us write L in terms of the principal moment of inertia. You see, I is now a diagonal one. And omega is nothing but omega x, omega y, and omega z. So this is simply ixx omega x plus iyy omega y. I guess you have done a lot of problem already in finding out the moment of inertia, the components of the moment of inertia. So I will not go in that direction much. Let's see what the kinetic energy becomes. So this is angular momentum. And these are all in principal axis. Now I am talking about kinetic energy. So how do I write the kinetic energy? Let's ask that question first. Kinetic energy is given by half mass of all the particles vi dot vi one of the vi, just like before, I can write as omega cross ri. And all these are true for any axis. Shortly we'll go to the principal one, but let's see. In general here. So this is A dot B cross C. I can write this as well as omega dot A my Ri cross Vi, and that you realize is the total angular momentum. So this is half omega dot L, and we have just written L in terms of the moment of inertia. So this is this. So this is a relation which looks almost like half mv square, where m is replaced by I and v is replaced by omega, but it's a little complicated because it's dot product and then tensor product, etc. But if I now, in terms of principal axis, this becomes simpler. Principal axis, what happens is, this can be looked as a product like this with I diagonal. So let me generate some space and write this. These are all 0 because I am in principal axis. And again omega x, omega y, omega z here. If you do this, it's very straightforward to do. So we'll get, well, actually we have already done this part. This part was Ixx omega x plus Iyy omega y plus Izz omega z. So this becomes, it's not plus, this is this. It's a column vector like this. So when I multiply that column vector with this row vector, what you will get is often written this way. So now you see that it has almost the form of half mass times velocity squared, or the mass replaced by the moment of inertia and the velocity replaced by the angular velocity. Very nice. So we know how to write down the kinetic energy, which we'll use the next time. Let us write down the equivalent Newton's laws for rigid body. And here I will not prove one step, because I guess that in your earlier studies you have done that, is that if I have a moment of a force that is equals to the rate of change of angular momentum. And I can use now my time derivative formula if I want to write these things with respect to the space set of axes. So n equals, I want to write this in terms of the space set of axes. So space set of axes equals, you will agree now, we have done it many times, this with respect to the body set of axis, how the angular momentum changes with respect to the body set of axis, plus the instantaneous angular velocity cross, I am doing the time derivative of L, so it is this. So n can be written as, what is L? Well, L is I times omega. Just let me write it here to remind you of this relation. And here I am doing a derivative with respect to the body set of axis. And the moment of inertia, the body set of axis, remember, we will always choose for our simplicity with respect to the principal axis. So body set of axis, there is a special choice for this, chosen along the principal axis. Of inertia. So there is a special set of axes, which is the body, which is the axis along the principal axis of inertia, that I have chosen as my body set of axis. So which means that I does not change. Well, it doesn't change because I has the information about how the mass is distributed in the rigid body. Like capital M is the total mass, I is how it is distributed in the rigid body, and because the body is rigid, it cannot change. The distribution of mass in the rigid body cannot change, which means when I write this dl dt with respect to B, it will be dl dt with respect to I omega. I can now come out. So I just get d omega dt with respect to B. And L I can also replace by I omega. So that equation is called Euler equation. This is called Euler equation for two reasons, because this is something which is equivalent to Newton's law for rigid body. And just like Newton's second law, this is the Euler's equation for rigid body. But this is also the equation that you will get if you would have used the Lagrangian method, and this would come out to be the Euler-Lagrange equation. Okay, just I would like to write down this as the component from 1, and that will be the end of the discussion today. So if you look at this, nx will come out to be, what will it come out to be? Well, in the first term, I have omega x, omega y, and omega z, and the component that I will get is ixx omega x dot and the second term, if you calculate, well, this I is just ixx, iyy, and izz diagonal. So it is easy to calculate. So I leave it to you to do that. It's an easy way to remember also. I have x over here. I put minus y, and then there are two omegas. There will be y and z, and write this cyclically. So x, then y and z. There is a minus sign in between. And here I will have again y and z, the moment of inertia, difference of them, the principal moment of inertia. So this way. So it's easy to remember. So it's y, so z, x, here also, z, x, z, omega z dot, x, y. So at the end of the day today, we have been able to write down the equivalent of Newton's laws for the rigid body in terms of the torque n, the instantaneous angular velocity omega, and the principal